Hello, I'm Matthew Beeler, one of the authors of Disorder-Driven Loss of Phase Coherence in a quasi-2D cold atom system. We present evidence that disorder can drive phase fluctuations in 2D systems, results that may help explain the superconductor to insulator phase transition in disordered 2D superconductors. Although discovered in 1987, the underlying mechanism that explains their superconductivity is still up in the air. High-temperature copper oxide superconductors are made of stacks of weakly coupled planes of atoms, and the physics of disordered 2D systems seems to play a large role in determining their material properties. We model the planes of the superconductor with two parallel surfboard-shaped atomic samples of well-controlled, ultra-cold gas. We show that the phase coherence of the planes vanishes faster than the fraction of coherent atoms as we increase disorder strength. This reveals that disorder drives strong phase fluctuations in 2D systems. These phase fluctuations, in turn, are expected to drive a transition from a high-temperature superconducting state to a normal state, but are hard to see in these materials. Our experiment begins with an optically trapped 3D Bose-Einstein condensate of rubidium-87 atoms, which we split into two uncoupled quasi-2D planes using intersecting laser beams. Disorder is introduced by optical speckle, which causes the atoms to be repelled from regions of higher intensity. We adjust the disorder strength by controlling the intensity of the speckle beam. To make measurements, we suddenly turn off the confinement and the disorder. The planes expand rapidly, overlapping and forming an interference pattern seen in absorption images. The visibility of these interference fringes tells us the phase coherence of our planes. Perpendicular to the interference pattern, we observe the momentum of the atoms and a two-component distribution, with the incoherent thermal atoms forming a broad background on which the coherent atoms sit peaked in the center. We measure both the temperature of our planes from the width of the thermal distribution, as well as the fraction of coherent atoms. We can adjust the initial phase space density of the atoms before adding the disorder, analogous to controlling the temperature in a solid. This allows us to produce two phase diagrams, with disorder strength along y and phase space density along x. One phase diagram shows fringe visibility, and the other shows coherent fraction. Without disorder, this fraction closely tracks the visibility of the interference pattern. However, as we increase the disorder strength, this is no longer true, as can be observed in the upper right corner of the phase diagrams, where the coherent fraction phase diagram is much darker than the visibility phase diagram. We can further quantify this by integrating the phase diagrams along the phase space density axis. Clearly, these two quantities stop tracking each other at high disorder strength. Although we don't see a phase transition in our relatively small finite system, our results show that disorder generically drives phase fluctuations in quasi-2D systems. These phase fluctuations are thought to be a mechanism behind the superconducting phase transition in high-temperature superconductors, and this is the first direct observation of disorder causing these phase fluctuations.